So I wanted to take a second and make sure that Timmy and Connor were caught up on these word problems that we were doing in class. Anyway, this is one of the ones we did. A farmer has 1,200 meters of fencing. He wants to enclose a rectangular field bordering a river with no fencing needing along the river. So in other words, he's got this from here to here is 1,200. There's 1,200 meters of fencing. Okay. Now, and he wants to find the maximum area that he can enclose because he wants to. So let's find a function. Let's create a function that models the area. And let's see what that's going to look like. So area, we know that area equals length times width. Well, let's see if we can figure out what the width would be. So if we called this the width, and this the length, and this the width, then we know that these three sides together equal this 1,200. So in other words, 2W plus L is going to equal 1,200. So I need to figure out this equation, but here I've got two variables, right? Here I've got the same two variables. So I want to get rid of one of the equations, one of them in here. So I'm going to substitute into here by solving in this one first. So I'm going to subtract 2W. I'm going to get L equals 1,200 minus 2W. So if I know that L relative to W, what that equals, then I can plug it in over here and say area equals 1,200 minus 2W times W. Now I can distribute that in, and I will get A of W equals negative 2W squared plus 1,200W. So now I have my function, and where area is a function of width. Okay. Now I want to maximize that because I want to make the most money that I can off of my fencing that I spent lots of money on. So I'm going to maximize that. Now we know that the maximum occurs at the vertex. So if I convert this to standard form, I will know lots of stuff. I will know my vertex. So I'm going to scoot this up just a little bit. Okay. So let's convert to standard form. And we do that by completing the square. So my first step is going to be to factor out this negative 2. So I'm going to factor that out. And I'll be left with W squared minus, well, what's 1,200 divided by negative 2 is minus 600W. Now, so to complete the square, I'm going to take half of this. 600 divided by 2 equals 300, right? And then I'm going to square it. 300 squared equals 90,000. So I'm going to add that here. Now, because I don't want to add anything over here, and I can't just add things to one side, so total, I'm going to add, what I actually added here is 90,000 times negative 2. So I actually added negative 180,000. Okay? And because I added negative 180,000 here, over here, I need to add the opposite of that. I'm going to add 180,000. Now, all total on this side of the equation, right? So I've got A of W over here, right? All total by adding negative 180,000 and positive 180,000, I've actually added 0 to this side total. Okay, and that's why I put this number out here. So I only add 0. Now I'm going to rewrite this. Remember that I'm going to rewrite this as a perfect square. and I've got this. So, in other words, the vertex of my equation is the point 300 and 180,000. Now remember, this is the width, and this is a area given that width. So then the maximum width, or the maximum area, is 180,000, and that occurs when W equals 300, or the width is 300. So let's go back to our original drawing here. So if this W equals 300, right, and this W equals 300, then this L must equal 600. So the dimensions of the field are 300 times 600. Which, if we check that, because remember that area equals length times width, then area equals 300 times 600, which equals 180,000. Okay, so some big numbers, but it's all there. And that's what most of the word problems are going to be like. They're going to ask you to write an equation, to model the function given a certain value, so you come up with your model, and then you're going to maximize that by rewriting it in standard form and finding that vertex. Okay.